So my topic is basically integrating fertilizer production into refining and petrochemical complex, driving towards sustainability. So before I start, just a little bit of introduction about Genesis. So Genesis is basically the consulting and advisory arm of Technip Energy. It is 100% owned by Technip Energy, but at the same time, it is independent entity with technology agnostic approach. And we are not a mere consultant. Our advisory services consist of both consulting as well as engineering capability. So whatever we suggest to our client, definitely we can engineer the same. And just to mention that in India, Genesis has completed 5 years of operation. Now moving back to my topic, that integration of fertilizer production into refinery and petrochemical. So as you know, there is a global pressure on the refineries to decarbonize, and at the same time, we're going for a transition to the EV. So obviously, there will be less demand of fuel, and we need to decarbonize. So by integration of petrochemical into refinery complex, to some extent, we're fulfilling this requirement. But at the same time, if we look overall complex, still there are good amount of streams, which are like low-value streams or so-called waste or effluent, basically like ammonia, H2S, carbon dioxide, etc. Those can be recovered and used as a feedstock for the fertilizer complex. So this integration basically that will create a circular economical model where waste become a valuable resource. Thereby we are reducing emission, we are reducing the raw material cost, and also we are enhancing the profitability. So I'll briefly cover about the background, the integration concept, or the technology available, simple case study, followed by opportunities and challenges, and finally the conclusion. So why I'm talking about fertilizer? Because if you see in the year 2023-24, total fertilizer consumption was about 60 MMTPA, and out of that 17.7 MMTPA was imported, which is almost like 30%. So in the right hand side, if you see urea, the import dependency is 13%, NPK 10%, DAP 60%, MOP, that muriate of potash, almost 100% we have to import. And there is a strong demand that this fertilizer will further grow, driven by the population, the food security, the expanding basically crop area, and the soil condition. So in order to make India self-dependent or self-reliant, basically, we need to produce more and more fertilizer. And there, this integration comes into effect. Like if we talk about the fertilizer complex, the key ingredients are ammonia, sulfuric acid, carbon dioxide. Like if we talk about urea, it is ammonia and carbon dioxide. If we talk about DAP, diammonium phosphate, ammonia and phosphoric acid. And how we are generating phosphoric acid? By reaction of sulfuric acid with phosphate rock. So the key ingredients are basically ammonia, sulfuric acid, carbon dioxide. How we are producing ammonia? By reaction of nitrogen and hydrogen. Nitrogen we are taking from air, hydrogen we are getting from the SMR. Similarly, carbon dioxide we are also recovering from the SMR in a fertilizer complex, and for production of sulfuric acid we are using sulfur. Whereas in the left hand side, if you see in the refinery what we are doing, the crude content impurities like nitrogen and sulfur, that nitrogen is getting converted to ammonia during this hydrotreatment process. And what we are doing, we are just burning that ammonia in the sulfur recovery unit. So in the fertilizer complex, there is a demand of ammonia, and on the other hand, in refinery, where ammonia is already available, we are just burning it. Similarly, sulfur that is converted to H2S, and we cannot release it to atmosphere, so we are forced to convert that H2S to produce basically sulfur. So this is not to make money, but to meet the stringent regulatory regulations basically. Same for carbon dioxide also. We are eliminating so much of carbon dioxide, we can easily recover those carbon dioxide and utilize it for the fertilizer complex. So thereby basically this low value streams can be used as a feedstock for the fertilizer complex. Thereby it can lead to additional revenue generation, so it will improve the economics, and it will also contribute to self-reliant India for fertilizer production. At the same time, this integration will lead to improve operational efficiency and flexibility, leading to reduction in the environmental emission. Now, how this integration is going to happen? Like, as you discussed in a refinery and petrochemical complex, also this basically, if we talk about waste streams, so ammonia, H2S, and carbon dioxide, these are the main waste streams. So what we are doing with H2S in refinery, we are converting H2S into solid sulfur, and then we are dispatching. And what is happening inside the fertilizer complex? They have to import sulfur, then solid sulfur, they have to melt it. We are burning it to produce carbon dioxide, then the carbon dioxide is converted to, sulfur dioxide, and that is converted to sulfur trioxide, oleum, followed by sulfuric acid. whereas H2S can be directly converted to sulfuric acid. Thereby, we can eliminate lot of intermediate steps. So there is no intermediate storage requirement. There will be no transportation, no sulfur melting, burning, etc. So there will be significant capex reduction, same significant reduction of plot area requirement, manpower reduction. At the same time, there will be ease of operation. There will be much better efficiency, leading to reduced carbon footprint. So, like if we see on the right-hand side, we need sulfuric acid. So as we discussed, we can directly convert H2S into sulfuric acid. So that means the sulfuric acid plant, which is required for the fertilizer complex, that can be eliminated. Next, we can recover this carbon dioxide and ammonia. Okay, the question could be, how much ammonia we are recovering? Is it good enough to sustain this operation of fertilizer complex? Certainly not. We need to produce more ammonia. Now, how we are producing ammonia? We need nitrogen and hydrogen. If you look at the refinery, there is HG unit already available to support the demand of hydrogen for the hydrocracking, hydrotreatment process, etc. So when you are integrating steam cracker and aromatic complex along with the refinery, the steam cracker and aromatic complex, they are hydrogen rich. So they are already exporting hydrogen to refinery. That means there will be spare capacity available in my HGU. Besides, we are going for more and more green hydrogen. That will also lead to availability of surplus hydrogen. So this surplus hydrogen we can send to the fertilizer complex. So that means the SMR, what is normally required for a standalone fertilizer complex, the capacity can be significantly reduced if we integrate it with the with the refinery complex. Similarly, we need nitrogen. We are generating nitrogen from the air separation unit. And in refinery also, we already have nitrogen, the air separation unit available. And normally, this air separation unit or nitrogen generation unit, that is designed for the governing case. And governing case is basically like for purging and for regeneration, etc., which is not like a normal operation. So during normal operation, there is a significant margin available or capacity available in the air separation unit. So that nitrogen, we can route it to the fertilizer complex. So thereby, if we integrate the fertilizer along with the refinery complex, that means not only the SMR capacity, but the air separation unit capacity that can also be reduced. So sulfuric acid plant we can totally eliminate, and at the same time we can reduce the capacity of both SMR and air separation unit. So one way there is a feedstock integration, so waste streams are getting converted as a feedstock for the fertilizer complex, and at the same time when we are integrating there will be shared utilities, as well as basically it will lead to much reduction in the capital intensity. So this integrated complex will have much lower capex if we compare with the standalone fertilizer and refinery complex. And at the same time, it will lead to a reduction in carbon footprint. Now question is, do you have the technology available to recover this ammonia, carbon dioxide, or conversion of H2S into sulfuric acid? The answer is yes. In each and every refinery, we have the sour water stripper unit, whether it is a single stage or two stage. In a two-stage sour water stripper, what we are doing, we are taking out H2S rich gas from the overhead of the first column, and from the overhead of the second column, we are getting ammonia rich gas. Now, depending on the recovery target, okay, there could be some low-cost modifications required, but the scheme, the columns are already available. We can easily get ammonia from the existing system with some low-cost modification. Okay, in order to meet the specification of the fertilizer complex, there is some treatment required for the ammonia. So there will be ammonium treatment of ammonia, followed by ammonia compression, liquefaction, etc. So with some addition of basically lower amount of capex, we can generate, we can convert basically this ammonia as a feedstock for the fertilizer complex. Similarly, if we talk about H2S, so yes, that can be directly converted to sulfuric acid. It is a licensed unit. There are several licenses available. I think my next speaker, he's going to talk in detail about this system, so I'm not going in depth, but the technologies are already available for conversion of acid gas into sulfuric acid. And for carbon dioxide capture also, yes, technologies are already available, whether you're going for amine scrubbing, whether it is a membrane separation or cryogenic process, the technologies are already available. We can recover carbon dioxide, we can capture it and utilize it for production of urea. So that will lead to the proper integration. And just to give a typical case study, simple case study, like let us consider one refinery and petrochemical complex of 10 MMTPA capacity. So in the feed, normally we have feed sulfur, let us consider average feed sulfur of about 1.25 weight%. So that can lead to production of about 1150 tons per day, that is almost 0.38 MMTP of sulfuric acid. Similarly, if we consider the nitrogen content, there is a potential to recover about 40 tons per day of ammonia, which is almost like equivalent to 6.6 million USD. And if we see in 2024, we have imported $1 billion USD of ammonia. So at least to some extent, we can recover ammonia and we can reduce this import dependency. If we consider overall refining capacity, 258 MMTPA, and if we recover ammonia from all the refineries, okay, the total ammonia recovery potential will be roughly about 0.34 MMTPA. That means something like $170 million. And utilizing this 0.34 MMTPA, if we want to produce some fertilizer, let us consider DAP, diammonium phosphate, because 60% of the DAP we are importing, which is about 5 MMTPA. So utilizing this 0.34 MMTPA of ammonia, recovered ammonia, we can generate 1.3 MMTPA of DAP, which is almost like 26% of what we are importing. That means based on the recovered ammonia from all the refineries, we can satisfy 26% of DAP import demand. And if we produce more ammonia, obviously we can go for the whatever total DAP demand we can satisfy. Otherwise also we can go for alternatively like ammonium sulfate production or ammonium phosphate sulfate production. There is a huge demand of all this fertilizer also. So basically if we go for the opportunity and challenge, yes, when we integrate this fertilizer complex along with refinery and petrochemical, it leads to a circular economy, basically reducing the overall capex, and at the same time there will be environmental impact, reduction of environmental impact. And when you talk about the challenges, okay, the first challenges will be the amount of ammonia, whatever we are going to recover. It is not a significant amount, so it will not be self-sufficient for the fertilizer complex. We need to produce more ammonia, but we already discussed there are surplus hydrogen and surplus nitrogen available inside the refinery. So utilizing that surplus hydrogen and surplus nitrogen, we can meet the additional ammonia demand also. Another point could be introduction of green hydrogen. Nowadays we are going for more and more green ammonia. So if we're going for more and more green ammonia, that means there will be less demand for SMR for the fertilizer complex. And SMR is not only supplying hydrogen, they are also supplying carbon dioxide. So there will be shortfall of carbon dioxide in case you are going for more and more green ammonia. But if we integrate a fertilizer complex along with this refinery and petrochemical, so we can recover carbon dioxide, and that carbon dioxide can be used as a feedstock. So we can leverage a carbon credit system basically for the integrated system. Third point could be higher solid handling. Yes, because we are producing so much of fertilizer, we need to have bagging, packaging, storage, etc. But thanks to our expertise in the petrochemical sector, we are already handling this solid. So there is no issue at all. It can lead to seamless operational transition and management. There is no issue related to handling of higher amount of solid. The fourth point could be like permitting and regulated hurdle, because there is a cross-sector integration. One side we have MOPNG, another side like a Ministry of Fertilizer. So that can be easily sorted out by early stakeholder engagement. We can establish a joint policy framework in order to address the concern early and basically facilitate a smoother approval and coordination process. As said by Albert Einstein, in the middle of every difficulty lies opportunity, and here we have the opportunity. And also, as said by Nelson Mandela, it's always seems impossible unless it is done. So this can be easily done. So moral of the story, refineries are facing challenges to reduce carbon dioxide emission, adapt to the evolving market dynamics, and simultaneously improving profitability. Integration of refinery and petrochemical to some extent address this concern, but there are some low-value stream available. We can recover all this low-value stream, use as a feedstock for the fertilizer complex. So when we integrate the fertilizer along with the refinery and petrochemical complex, it will lead to like a circular economy leading to better profitability. And if we talk about the key enabler for success, the technologies are already available. There is no issue at all. There is a very good demand for the market for all the fertilizer products. And with valorization of this low-value stream and producing a higher value fertilizer, it will lead to greater economical resilience. There will be much less capex requirement, much less area requirement, plot plan requirement, basically manpower requirement will be optimized, and thereby it can lead to significant reduction in the carbon footprint. And ultimately, we will be able to contribute to self-reliant India for the fertilizer production. So this integration of fertilizer with refinery and petrochemical complex, so it is creating basically a circular economical model where these low-value resources or waste streams are converted as a valuable feedstock product, reducing the emission, reducing the raw material cost, improving the overall efficiency, leading to better utilization of the existing OSBL system as well as the existing facility, and thereby overall profitability is going to increase. So it will make sustainable. So being part of Genesis and Technip Energy, will be happy to help in this integration process, whether it is from the early stage engineering, preparation of pre-feasibility study, feasibility study, basic package preparation, licensor selection, or detail engineering, feed, EPC, etc. Because in Genesis and Technip Energy, we believe that sustainability not only reducing our own carbon footprint, but to assist our client to help them to attain their sustainability target, to achieve their goal for the decarbonization, to increase basically the efficiency of their existing system, and thereby making it much more profitable. So why to wait for? Let us break boundaries together and engineer a sustainable future. Thank you very much.